What specific problem does Depth Pro aim to solve in the context of zero-shot monocular depth estimation, and what are the key challenges that the authors identify in existing methods?
Depth Pro aims to solve the problem of producing metric depth maps with absolute scale from arbitrary images in a zero-shot manner, without requiring camera intrinsics or metadata. The authors identify several key challenges in existing methods, including the inability to generalize beyond specific domains, the lack of accurate scale and shift in depth predictions, and the production of low-resolution depth maps that fail to capture fine details, leading to issues like flying pixels. Additionally, they highlight the need for low latency in processing high-resolution images to support interactive applications, which many existing methods do not achieve due to their computational demands. Depth Pro addresses these challenges by employing a multi-scale VIT-based architecture that captures both global context and fine structures, enabling it to outperform prior work in boundary accuracy and processing speed.
How does the proposed Depth Pro algorithm work? Illustrate step by step, from input image processing to output depth map generation.
The Depth Pro algorithm processes an input image through a multi-scale architecture that employs vision transformers, VITs, to generate a dense depth map. First, the input image is downsampled to a fixed resolution of 1536 by 1536 pixels, and then it is split into overlapping patches at multiple scales. Each patch is processed by a patch encoder, which captures local features, while a separate image encoder processes the entire image to provide global context. The outputs from these encoders are fused to create a high-resolution depth map, which is then scaled to produce a metric depth map by estimating the horizontal field of view from the image features. Finally, the algorithm outputs a 225 megapixel depth map in just 0.3 seconds, ensuring sharp delineation of object boundaries and fine structures.
Can you provide a simple yet illustrative example of how Depth Pro generates a metric depth map from a single input image, detailing how it addresses shallow details such as hair or fur during this process?
Depth Pro generates a metric depth map from a single input image by employing a multi-scale vision transformer, VIT architecture that captures both global context and fine details. The model processes the input image at multiple scales, allowing it to maintain high resolution and accurately delineate intricate structures like hair and fur. Specifically, the architecture includes a patch encoder that extracts overlapping patches at the finest scales, which helps in preserving sharpness and detail during depth estimation. Additionally, Depth Pro utilizes a training curriculum that emphasizes the importance of sharp boundaries, focusing on gradients of predictions to enhance the accuracy of depth maps around fine structures. This combination of advanced architecture and targeted training enables Depth Pro to produce high-resolution depth maps that effectively trace and represent shallow details, thereby improving the quality of applications such as novel view synthesis.
What theoretical or practical benefits does Depth Pro offer compared to prior methods in monocular depth estimation? Please specify in terms of accuracy, runtime, and boundary tracing.
Depth Pro offers significant theoretical and practical benefits over prior methods in monocular depth estimation, particularly in terms of accuracy, runtime, and boundary tracing. In terms of accuracy, Depth Pro produces metric depth maps with absolute scale on arbitrary images without requiring camera intrinsics, achieving 1 to 2 orders of magnitude better boundary accuracy compared to previous state-of-the-art methods. Regarding runtime, Depth Pro operates at high resolution, generating 225 megapixel depth maps in just 0.3 seconds on a V100 GPU, making it substantially faster than other approaches that often struggle with high-resolution images. Additionally, Depth Pro excels in boundary tracing, demonstrating unparalleled sharpness and delineation of object boundaries, including fine structures like hair and fur, which is crucial for applications such as novel view synthesis. Overall, Depth Pro's architecture and training curriculum enable it to outperform existing models in these critical areas, providing a robust solution for zero-shot monocular depth estimation.
How is the Depth Pro model validated or tested? Discuss the experimental design, datasets used, and metrics for performance that demonstrate the effectiveness of the method.
The Depth Pro model is validated through a comprehensive experimental design that includes comparisons against state-of-the-art monocular depth estimation systems in a zero-shot setting, meaning it is evaluated on datasets not seen during training. The datasets used for testing include Booster, Middlebury, SunRGBD, ETH3D, Nucines, and Sintel, which were selected to ensure a diverse range of scenarios and to avoid domain bias. Performance metrics for validation include the one metric, which measures the percentage of in-layer pixels where predicted and ground truth depths are within 25% of each other, as well as boundary accuracy metrics that assess the sharpness of object boundaries in the depth maps. Depth Pro consistently scores among the top approaches across these datasets, demonstrating superior boundary recall and accuracy, particularly for fine structures like hair and fur. Additionally, the model's focal length estimation capabilities are evaluated on a curated zero-shot test dataset, showing it outperforms other methods in accuracy across various image sources.
What are the inherent limitations of the Depth Pro method, especially concerning its zero-shot capabilities or performance in varying conditions?
The Depth Pro method, while advanced, has inherent limitations regarding its zero-shot capabilities and performance under varying conditions. Firstly, although it operates without requiring camera intrinsics, its reliance on the quality of input images means that poor image quality or extreme lighting conditions could still affect depth estimation accuracy. Additionally, while Depth Pro excels in boundary tracing and sharpness, it may struggle with complex scenes that contain occlusions or intricate details that are not well represented in the training datasets, potentially leading to inaccuracies in depth perception. Furthermore, the method's performance is contingent on the diversity of the datasets used for training. If the model encounters scenes significantly different from those in its training data, its zero-shot performance may degrade. Lastly, while Depth Pro is designed for high efficiency, its computational demands may still pose challenges in real-time applications, particularly when processing high-resolution images in less than a second.